I mentioned bond energies in the last video, so let's talk about bond energies. Bond energies do exist in tables as data that we can use, and when it's listed, it's the energy required to break 1 mole of bonds in the gas phase. We usually see these reported as average bond energies. So, an a bond energy can vary across compounds. So, if you imagine a carbon hydrogen bond, you can have a ton of different molecules that have a carbon hydrogen bond. And depending on what that carbon is also attached to, it can change the energy of that carbon hydrogen bond. However, it is close enough that we can use these average bond energies and tabulate that data and use it to get useful information about reactions and compounds. What you will see and what these mean is that if you have a higher value for the bond energy, this means that it's a stronger bond. We can use the bond energy to find delta H reaction. So we will use, it's going to be marked as delta H reaction. It's not going to have that little circle on it. And if you're looking for a how do I know when to use bond energies, if it's the only thing you can access, then you can probably use it. And I will probably tell you. I'll either say use bond energies to find this, or a previous part of the problem will have the standard enthalpy of reaction for which you can use enthalpy of formation. And then the next part will say find delta H reaction in a different way. This will be the only other way that you have to find it. So the reaction we're going to look at is CH4 plus Cl2 making CH3Cl and HCl. Everything is a gas, so great. The way that the delta H reaction is calculated, it is the sum of the bonds that are broken minus the sum of the bonds that are formed. Now, I have a second version of this equation only if you happen to be referencing the TRO textbook. They like to say delta H reaction is equal to the sum of the bond energies of the bonds that are broken plus the sum of the bond energies for the bonds that are formed. Now, this clearly looks like it's going to give you two different results. It will not. They are expecting you to put in the negative for the energies of the bonds that are formed because your energy is given off when you form those bonds. Either equation is fine. Just keep in mind like which one you're using and what you need to do for it. So for the top reaction, I've got a star by it. It's definitely the easier one. You can just dump all the numbers in, but you need to be cognizant of the fact that when you break a bond, you put in energy. When you form a bond, you get out energy, and that needs to be accounted for. So in this reaction, what is happening? Well, let's draw Lewis structures to see what's happening. I have CH4, carbon, 4 hydrogens around it, Cl2, which is just chlorine with a single bond between them, making CH3Cl and HCl. So I have all of these Lewis structures. The things that changed, it looks like I broke the carbon hydrogen bond in CH4 and I broke up my chlorines. And then I took one of the chlorines and connected it to the carbon and the other chlorine and connected it to the hydrogen. So the bonds that were broken, I broke one carbon hydrogen bond and one chlorine chlorine bond. And these values, that 414 kilojoules, 243 kilojoules, those are in the table. That's where those numbers came from. I formed a carbon chlorine bond at 339 kilojoules and a hydrogen chlorine bond at 431. One of each. This needs to be negative, so I can either use the form of the equation that has a negative sign, dump everything in, which is I only have 1 mole of each, so I don't have to do any multiplication. But right, this is the delta H of the bonds broken. You do have to account for how many of them were broken. I've just got 1 mole of each, so 414 plus 243, and then I'm going to subtract 339 plus 431. I get a delta H reaction of negative 113 kilojoules. Now, if you like the TRO version, I also have it written here underneath showing where you would be expected to put the negatives in for that version. You still get negative 113 kilojoules. And let's do a final example where we do have to worry about the number of moles. So we are going to use bond energies to calculate the delta H reaction for CH4 plus 2H2O turning into 4H2 plus CO2. So I don't have Lewis structures drawn here. Because of the way our equation works, where we are
stop and draw the Lewis
putting in
structures,
energy to
make sure
break
that
bonds,
you can account
and we're
for
getting energy back
all
out when those
of
bonds are
the
formed.
bonds that I'm going to
And
list out for you that would
the
need to go
amount of
into
energy
this.
has the same
So
magnitude.
if you
with the
lay out your
opposite
Lewis
sign.
structures,
If you break a
and
bond
count the
that
number
you
of
didn't
look
need
at what
to
bonds are
break,
breaking, what are
when you
forming,
reform
count the
that
numbers of
bond,
each,
the
you're
energy
going
will
to
cancel
break
out.
all
So if you
four
break
carbon-hydrogen
everything
bonds,
and then form everything, you will break
if
a
there are some
total of
redundancies or
4
some things that you didn't
oxygen-hydrogen
need to
bonds.
break, then everything will be taken care
This
of.
is because each water has 2 oxygen-hydrogen bonds and there are 2 waters. So you have to account for every single one of those bonds. We're going to form 4 hydrogen-hydrogen bonds, and we're going to form 2 carbon-oxygen double bonds. And I have a star by this because there will be a star by it in the table that you look at. Make sure that you are accounting for the fact that these carbon-oxygen double bonds are in carbon dioxide. In the end, you should get a delta H reaction of 170 kilojoules. So try this out, see if you get 170 kilojoules, and if not, let me know so we can figure out why you didn't. Now, in this reaction, we did break every bond and then make every bond in the reactants and products. However, my pro tip for doing bond energy calculations is that when in doubt, break everything and then reform everything.